Thanks, Lisa. Hi, hi everyone, or good evening, good morning, good afternoon, wherever you are. It's morning here in New Zealand, where I'm talking from. But I'm always excited to talk about my research and pleased to share it. So, as Lisa mentioned, I'm going to talk about IceCube, which is a neutrino detector. So here is to set the scene is where IceCube is. It's at the South Pole, but it's actually below the surface. So I'm gonna tell you more about it. I'm gonna start, but I just to get you orientated of what I'm talking about. So here is the ice pole, the South Pole, and this is the cross section of where IceCube is, but the actual neutrino detector is below the surface. So this is a cartoon, which I will show you again later in the talk. But just as I said, to sort of get you orientated of what you're hearing about, this is our detector. It's between 1.5 kilometers and 2.5 kilometers below the surface, and it's an array of detectors to detect neutrinos. So I start as Lisa didn't mention, but I'm part of a collaboration. So I'm talking about this research, but it's a large collaboration of people that work on this project, of engineers, astrophysicists, computer programmers, and lots of graduate students to do lots of work. So we're in around 50 different institutions right across the globe. So I'm talking about the research and sharing it, but it's certainly not my research alone. It's a large project with lots of people contributing, and actually that's a big part of what I enjoy about working in IceCube, is that we're a team together working on this research. So yeah, basically what you're going to hear about is doing astronomy. So it is astronomy that I'm mostly going to talk about with neutrinos, so our messenger particles telling us about the cosmos. Our neutrinos, and we're detecting them at the South Pole. So that's in a nutshell what I'm going to talk about. So I'm going to start talking about neutrinos, and if this was a live talk, I usually start kind of gauge the audience and you know, where they're at and what I'll ask them, you know, neutrinos, what do you know about them, to see. And obviously it's not going to work today, but these are kind of, I could guess, the sorts of from past talks, the sorts of things that people would say. So I'll just, in case you're wondering, over on the side here is a little image. This is from a competition that was run by another neutrino telescope, not actually IceCube, but the one in the Mediterranean. KM3Net collaboration, asking people to draw images of neutrinos. So a competition. This was one of my favorites, which was actually second place. So neutrinos, I think, to a lot of people, they're ghost particles. They are neutral. So the part of neutrino is they're neutral. They've got no electric charge. And so this ghost particle is that they're extremely weakly interacting, and I'm going to talk a little bit more about that. What else people say? They're a fundamental particle. So neutrinos aren't made up of anything else. They actually very like the electron. So you know about the electron usually, and in the standard model of particle physics, they are like a partner to the electron and its heavier siblings. So they are very similar in that way, but the big difference is that they are a neutral particle. Have a very small mass, extremely small, so that we don't actually know what it is, but we do know they have got a mass. They are created in radioactive decays. So that's how they were sort of first discovered or realized that they existed, was in radioactive decays. The sun produces a lot. They're produced in the same reactions in the sun that produces light, produces copious amounts of neutrinos. And you might know that there are 3 types of neutrinos actually which is related to their partners in the standard model. There's electron and muon, tau, neutrinos. So that won't be too important in this talk. It's mostly that I'm going to talk about them being messengers, and for that, the kind of crucial bit is that they are so weakly interacting, really, and this is what makes them unique. So some kind of fun facts or things you might have heard about neutrinos is that we all emit around 350 to 400, depending on our mass of neutrinos per day. That's from potassium 40, so we all have a small amount in us, and it's radioactive and it's decaying. So we are definitely sources of neutrinos. The sun produces a lot more neutrinos. So that's sort of a trillion in American trillions, so 100,000 million neutrinos from the sun for every thumbnail per second. And so that's day or night. I think the sun has gone down over London, over Britain now, and it's risen here, but we're basically getting the same number of neutrinos through us, through me and through you, wherever you are on the Earth. Because the neutrinos, unlike the light, you can't see the sun maybe anymore in London, but the neutrinos are not stopped by the Earth, so they're still streaming through. So that's the kind of interesting or unique thing about neutrinos. So I want to just talk a little bit about this weakly interacting nature, and the fact that they are passing basically unstopped through the Earth. So yeah, neutrinos, for that reason, and that image is a ghost particle. So ghosts can pass through walls, and how can that be, I guess? So here I've got an image of Ernest Rutherford, who is in New Zealand. We're very proud of Rutherford, as he was born in New Zealand. And this, actually, I just checked as well, and this image actually comes from the Royal Institution homepage, because he was also the professor of natural philosophy at the Royal Institution. And so Rutherford did various experiments, but one of the things he kind of basically told us was that with his famous gold foil experiment and firing alpha particles at this gold foil, and many of them went through, but some of them came straight back. And from that, Rutherford deduced that there was a central part of atoms, the nucleus of an atom, that had most of the mass, most of the guts of the atom was in the central part. And Rutherford thought it was at less than around a 3,000th of the volume of the atom. Now we know that nucleus takes up less than or around 1/100,000th of the volume of the atom. So this is the kind of image that you have. So if you're thinking of a grain of sand, which is maybe a sort of a millimeter across, then, and that's the nucleus, then you need a kind of 100 meters around if you've scaled up the nucleus to the size of a grain of sand. So you have a grain of sand in the middle of a football field. That's kind of what an atom is like, and all the guts is in that grain of sand, and the rest is just empty space. So that's what Rutherford told us, that matter is mostly empty space. And of course it doesn't really feel like empty. This doesn't feel like empty space to me. And that's this table which my computer is on. And that's because there is electrons as well. We have electrons in our hands, electrons here, and electrons don't like to be in the same place as other electrons. So those electrons make it feel like it's pretty solid. But actually, Rutherford did point out to us that it really is mostly empty space. So it's for the neutrino that isn't an electron, doesn't have an electric charge. That's what the Earth looks like. The Earth looks like that, mostly that empty space that it is, because it's really all about the interactions that make things look solid, make things feel solid. So with a neutrino, which doesn't interact very much, that's what the Earth looks like, just empty space with that little grain of sand in that ratio of grain of sand to football field kind of size. So once you kind of appreciate that, or kind of have that image in your mind that space is mostly empty, and if I'm not going to interact with it like an electron does with electrons, then I think it's kind of easy to see the neutrino just streaming through this mostly empty space. So that's a little bit the way the neutrino sees the world, the Earth, the universe is this empty space. But every now and then it can meet that grain of sand, and then it will interact. And that's kind of crucial, because otherwise we would never detect those neutrinos at all. They have to be the time that they hit the grain of sand, they meet the nucleus, and then interact, that we get a chance to actually see neutrinos. So just to kind of emphasize more on that point, other kinds of particles are viewed and with particle accelerators and looked, you can get tracks. I mean, nowadays a bit fancier than this kind of cloud chamber track, but you can see the path of the particle as it passes through the medium and ionizing or whatever it's doing. The particle is to be able to track. But neutrinos, there are no tracks. They're passing through you and me, as I talked about. They're not leaving any scarring in our body, no tracking. These kind of tracks are only when there is an interaction. So if there is no interaction, you just don't see it. So to detect neutrinos, we have to wait until they interact. And then the idea is that we never actually see the neutrino itself. We deduce that they were there by looking at the products of that interaction. So wait for the neutrino to interact. When it interacts, we'll see the products, and then we look, and from the information from the products, we can deduce information about the neutrinos. So there's a little bit to orientate a little bit more about the kind of neutrinos that I'm going to talk about, or that IceCube is interested in studying and observing. I'm going to mention other kinds of neutrinos as well. I already mentioned that human bodies are sources of neutrinos, and the sun is a source of neutrinos. So here on this slide, I've got at the top some images talking about different places, different origins for neutrinos. And here in the middle of the slide is an energy bar. It's in electron volts. It doesn't really matter too much if you can see the scale. So we're going from 1 million here, and then we're going up in factors of 1,000 in energy. So, and then arrows kind of pointing to where those energies of those kinds of neutrinos are. So solar neutrinos, the neutrinos from reactors, the neutrinos from our bodies, they are around here at this 10 to the 6 electron volts in energy. The energy neutrinos that IceCube is interested in looking at are the neutrinos, and I'm going to talk more about this, that are messengers from the high energy universe coming, we suppose, or we propose, from high energy objects out in space. And so they are predicted, or should have energies some million times more than these solar neutrinos. And along the bottom and here as well, there is names of a whole lot of different detectors. So I don't know if you read some popular science stuff, or you've heard other neutrino talks, you might have heard about some of these different neutrino detectors. There's lots of neutrino detectors, and as you can see here, and this is kind of showing the energy range that those neutrinos detectors operate in. So I'm going to explain a little bit more why a detector, or why a detector can't see neutrinos of all different energies if I have a neutrino detector. These ones that are operating in this range, detecting primarily solar or reactor, sometimes these atmospheric neutrinos that I'll talk more about later, but these in this range, they're often actually studying the neutrino itself. So the particle properties of the neutrino, because it's such a unique particle in the standard model, we believe that understanding those neutrinos will help us learn more about what physics there is beyond the standard model. It gives us clues as to why does the neutrino have such a small mass? What in the standard model gives the neutrino such a small mass? The kind of building those kind of models needs to do lots of studies of neutrinos, and that's the sort of primary goal of these detectors, these neutrino detectors here. And that is something we do with IceCube as well. But actually, the design of the detector, the first aim for the detector was actually not really to do to worry about the neutrino or study the neutrino, but to have the neutrino as a messenger from outer space. So use the neutrino very like electromagnetic radiation is used to study outer space. So that, as I mentioned, was much higher energy neutrinos that we are after with IceCube. So I'll talk again. Here is a bit about detectors and the fact that we have this very large detector, or the largest neutrino detector. So on that other slide, and some of the detectors for neutrinos that you might have heard about before is the Kamiokande detector, for instance, or the Sudbury Neutrino Observatory, this one in Canada and this one in Japan. So those are, as I mentioned, a study primarily the neutrinos from the sun, or these atmospheric ones, lower energy neutrinos than IceCube is after, in fact. So these ones, just to give a little bit of an idea in the scale there, those detectors, if they were kind of put beside IceCube, they're large. They're really large tanks of water, but compared, IceCube is much larger. It's a cubic kilometer. So these, whenever you want to detect a neutrino, as I mentioned, you have to wait for the neutrino to interact with that grain of sand in the middle of the football field. So you want lots and lots of grains of sand, lots of nucleons there to give you a good chance to detect neutrinos. So you always require a large detector. So these were large tanks of water to get a chance to detect those neutrinos. But to go with the astrophysical neutrinos, we needed an even larger detector. So here I have a graph. I think I'm guessing from this audience will be fine with this graph. I was once told in astronomy talks that every time you show a graph, people think it's a constellation in the sky and they're looking for the stars in the sky or something. But I'm picking that this audience will be okay with some graphs. But I'll explain anyway. This is a spectrum graph. So on this axis, on the vertical axis, we have flux. So that's just telling us how many per some units. So how many we're getting per second per some area units. So that's on the vertical axis, and on the horizontal axis is the energy. So here I talked about these solar neutrinos that come from the sun, and those detectors we're looking at. And here, these are just actually predictions for the astrophysical neutrinos that IceCube was constructed to observe. So there's kind of two things to look at on this graph, and one is that these, as I mentioned before, are much higher energy neutrinos that IceCube is after. The other is to notice that this line is some million orders higher than these lines here. So there's many more of these solar neutrinos coming through us than these astrophysical neutrinos. So that is the crucial reason why, if we go back to this, that we need to have this much larger detector. Actually, as neutrinos go up in energy, they interact a bit more. So we do win some that we're aiming for the higher energy neutrinos, so they get a bit more interactive as they get higher in energy. But this fact that we're looking for something much rarer means that these small detectors here, they might have a chance to see an astrophysical neutrino. There's no reason why one couldn't interact in them, but they would just have to wait so long for that chance to happen, because those neutrinos are rarer. So that's why this kind of detector, this huge kind of detector, is needed for the astrophysical neutrinos. Just need to, basically because they're rarer and we need to go up in size. The other thing to notice here, and I'll talk more about our detector, but these, if we go back, this tank of water is surrounded by photomultiplier tubes, which are light detectors. So as I mentioned, to detect a neutrino, you have to wait till it interacts, and then you detect the products. And those products produce light. And so that's what's actually detected by the Super Kamiokande and our detector. And so all these little white dots here are those photomultiplier tubes just surrounding that tank of water, and they're going to collect the light if and when a neutrino interacts. Here on this, remember, different scale, this is teeny compared to this. These black dots are our photomultiplier tubes. So you can see that we have a much sparser detector. Our instrumentation is spread much further apart. So we went for volume because we needed that to get a chance to see these rare neutrinos, but we don't have as denser packing of these light detectors, and that means that we don't see the lower energy neutrinos. So as a neutrino interacts, it produces these other particles and they produce light, and the amount of light that is produced is related pretty directly to the energy of the neutrinos. So a low energy neutrino doesn't produce much light compared to a high energy neutrino. So if a solar neutrino, which it undoubtedly do interact in our detector, we don't see them. They produce too little light for our detector to reconstruct them. So if they happen to be close to one of our light detectors, then we might get light on one of our sensors, but that's not enough for us to do anything with, and we call it trigger. We don't capture those events where we only see light on one sensor. So to get something to detect solar neutrinos, you need to have a much denser array and of your light sensors, so that you can get the smaller amount of light compared to the amount of light produced for the astrophysical. So we can get away with having this sparser detector because we're aiming for these higher energy neutrinos that produce much more light. So that's going back to the slide that showed the different detectors, kind of give you the idea of how different detectors are aimed in different energy regimes by their construction. So yeah, let's go on and talk now a bit more about IceCube. I've been mentioning. So these kind of grey lines here are cables. So there is around 86, we call them strings, of these cables that are deployed from the surface down 1.5 to 2.5 kilometers under the surface. And on these cables, we put these, you can see one down in here, these light sensors, so photomultiplier tubes that collect light. Said it's like a reverse of a light bulb. The light goes in, an electric signal comes out. So these are pretty standard light sensors, pretty good quality ones. So and they're in, I can see in here, in a glass canister, sort of around kind of basketball size, and the light sensor is there, and there is pretty high powerful computer in there as well to digitize that signal, do a little bit analysis before then it's sent up. The signal is sent up to the surface to our laboratory, which is on the surface. So there is, as I said, 86 of these strings. There are around 125 meters apart horizontally, and then on each of the cables there are 60 of these glass canisters with the light sensors, and they're 17 meters apart vertically. So we have this array of around 5,000 of these sensors distributed over around a cubic kilometer of volume, and these were deployed over a number of years at the South Pole, because it's only really practical to do things in the summer at the South Pole. And so these holes were, we say, drilled, but although the first part of the hole is a real hole, the you can't drill a hole 2.5 kilometers deep. It will collapse. But so these are actually melted. So with a hot water drill, so we melted a hole down to nearly to the bedrock. The ice is actually the clearest down the bottom, so that's where we wanted to get to, but we definitely didn't want to hit the bedrock, because then we would get dirt and crud into our melted cylinder here. So once we have this melted cylinder, we can lower the cable with these instrumentation attached and just lower it down into the melted hole. It takes around a day or so to melt each hole, and then we have a sort of a couple of days, no more, to lower the cable in. After that, it starts to freeze. It actually takes a good 3 months for the full hole to freeze again, because ice is actually quite a good insulator, and so it does take a while for that to freeze in. But you start to get sort of fissures, and so we could get our cables caught. So we have to be careful to lower them down carefully in that time period. So you can see there's a sort of good 3-day kind of turnaround at least per cable. So that was done over a periods of years. We could use the detector in its partial size as it was being built. So through the other parts of the year, we could be already starting to detect neutrinos, looking for neutrinos with our partial detector. But it wasn't until actually 10 years ago that we completed the detector with this, and this was the size that we had been predicted to would be needed to see those astrophysical neutrinos. So going back to that flux graph that I showed, and those were theoretical predictions for astrophysical neutrinos, which I'll talk a little bit more about why people even thought there should be astrophysical neutrinos in a bit. But that from those predictions, it was, you can do the calculations of how much neutrinos interact and figure out how big a detector you would need to actually be able to see those neutrinos. And this was the size, and actually pretty much as soon as we got to that requisite size, we did actually start detecting neutrinos. So that is our detector. The ice is extremely clear down, so we need to know where our strings are in the ice, where each of these are, so that we can well reconstruct the neutrino events from the light that we collect. And so we actually have inside this capsule, we also have little LEDs that we can flash, and then we can use for calibrating where exactly each of these is, so that we have a good kind of geometry layout of this array of detectors. Okay, I think I'll go on from there. Here's definitely a kind of artistic image of what it might look like if you could go down into the ice. These don't really look like they're 125 meters apart, but then the ice is very clear. So this is kind of what you can imagine, this array of light sensors distributed through the ice. And here is another image of what it kind of might look like when a neutrino interacts. So I mentioned that we detect the light from the products produced when a neutrino interacts. So as I said a few times, you don't see a neutrino itself at all, but if a neutrino interacts, it can produce charged particles. And those charged particles are actually traveling faster than light does in ice. So never faster than light does in the vacuum, but actually very close. They're highly relativistic particles, they're very energetic neutrinos and highly relativistic particles that are produced. So the particles themselves are traveling pretty close to that ultimate speed c, but in ice, light only travels sort of around a half of that speed. So the particles are traveling faster than light itself. And that's then something like a plane that's that's traveling faster than the speed of sound, they produce the light analog of a sonic boom, and that light is called Chirenkov light. So it's kind of, you imagine it, the electric field from those charged particles kind of gets bunched up as it can't get away as fast through the ice as the particle itself is traveling through the ice, and so you get this kind of bow shock wave, which if you do the calculations, you find is peaked. It's electromagnetic radiation, and it has a range of wavelengths, but it's peaked in the visible and in blue light. So you would actually, and you can see near some particle dumps for man-made particle accelerators, and then the dump, that you can actually see this sort of airy blue light. And so that light is got a direction associated with the direction of the charged particle, and it comes out, and then that's the light that we detect with our sensors. So here I have a little animation to show. So this is this red thing is going to be a neutrino that's actually going to interact with a nucleus. So actually, for those who know, it interacts with a quark inside an atom, inside a neutron or proton inside an atom, and that neutrino interacts and produces a charged particle that travels through our detector. So let me just start that animation. So there's the interaction, and there's the charged particle traveling through the detector, and you saw that sort of image cartoon, obviously, of the blue light produced and then detected in our array. So kind of mentioned, and so this is the only time that there are 3 types of neutrinos that are associated with electron, muon, and tau. So electrons, I hope everybody kind of at least knows something about. They have heavier siblings called muon and tau that very, very similar, same negative charge, but just a bit heavier. And there's neutrinos that match with each of those particles. So there's electron type neutrinos, muon type neutrinos, and tau type neutrinos. And so when they interact, they actually can produce their charged partner. So an electron neutrino interacts, produces an electron. Muon neutrino interacts, produces a muon. Tau interacts, produces tau. And what happens next depends on those different particles. So an electron interacts very readily and actually doesn't travel very far in the detector. It makes a cascade of particles, a shower of particles, all that produce light. So we detect those as well. But the ones that are really good for astronomy are these muon neutrinos producing a muon. So if I just go back again, in this case, this would have been a muon neutrino, and that was a muon that was produced, because muons can travel around kilometers through the ice. And so that you can see with this muon that's traveling through, we get a good direction, and that muon is very close to the direction of the incident neutrino. And you can see just sort of by eye that you could trace a line through the path of the muon, which lines up with the path of the neutrino, and you can start to see how you could do astronomy then, because now we have a direction. So I'll talk a little bit more what all these little coloured things there's mean in here. So it's just a cartoon, and we're showing here which of our sensors detected some light. So the light emanated out, and some of the sensors saw that light, and the colouring is just based on the timing, red through to blue, on which sensors saw the light first, and then the sort of little bit size that you can see there is related to how much light was detected by each sensor. So this is actually we will have this recorded in our data, and we use routines. We've got lots of PhD students coming up with new and advanced and better reconstruction routines, often to figure out from this light pattern here, from this information based on the timing and the amount of light, the path that reconstructs. But as I said, by eye, you can see that you can get that direction. So here is a actual event, and I'm just really repeating here some of those things that I said. So we can see the path that's been reconstructed here based on this, this light that was detected in the different sensors. And we can use the timing and the amount and say which path fits best with that pattern that's produced. We can also work out from the amount of light the energy. So it's actually harder with these muon ones to work out the energy, because the muon could have been passing somewhat through the surrounding ice before it reaches the detector. But we can definitely make estimates then for the energy of the original neutrino that produced this particle and the direction from this pattern of light that we see. So that's basically how IceCube works. And here I've got another real event where you can see this time a neutrino interacting. Well, you can't see the neutrino interacting. What you can see is that, or we can deduce that a neutrino interacted inside the detector, because we now see this particle traveling out from the detector. And so this is obviously slowed right down. The particle would be just a flash in nanoseconds, actually, because it's traveling close, as I said, to the speed of light. But we can then slow down for us. We could see the particle traveling out through the detector, and I think kind of by eye that you could see a direction associated with that. So that's what we built IceCube. What we aim to do is and detect neutrinos that way. So I said aim for IceCube was to detect astrophysical neutrinos, but before IceCube came along, nobody had detected any high energy astrophysical neutrinos. Some neutrinos have been detected from supernova. They're much lower energy, actually similar kind of energy to the neutrinos from our sun, but it was predicted that there should be astrophysical neutrinos. So I mean, sometimes it's just kind of think, hey, maybe there are these things. Let's build a huge $million detector, and we'll look for them. But usually you can't get funding agencies to give you those millions of dollars to build something unless you've got a pretty good case for why you should be able to see astrophysical neutrinos. And so, what was that case? Well, IceCube was really constructed to kind of solve a mystery about cosmic rays. So cosmic rays, hopefully you heard something a little bit about them. They're high energy particles, and we have detected them bombarding the Earth from space. So there is they have been detected, these cosmic rays. Early on, the first detectors would actually done in balloons, and this radiation was seen that as at first it was thought it was radiation perhaps from the Earth, but then as the people went up in balloons, Victor Hess was the name of the man, and he saw that this radiation actually increased as he went up in his balloon. And these cosmic rays actually come from a range of energies, and the lowest energy ones are solar particles from sort of solar storms, and then there is a range of energies up into some that we believe these cosmic ray particles are accelerated in the remnants of supernova that went off in our own galaxy. But then we get up to the highest energy cosmic rays, and we don't know where yet. Maybe we have now some clues that IceCube has been a part of figuring out, but at least when IceCube was promoted and first proposed, we didn't know where those cosmic rays. So very high energy cosmic rays detected with big cosmic ray detectors, various ones. This is one in Argentina called the Pierre Auger detector, and they detect the cosmic rays. Luckily, cosmic rays interact in our atmosphere. So you have to go up in space if you want to detect them directly, but they create a shower of particles, and you can detect those shower of particles with an array on the surface like this, and from that deduce the energy of these cosmic rays. So as soon as there's cosmic rays going up to extremely high energies, so actually millions times more energetic than, for example, the particles that have been produced in the Large Hadron Collider. So the question is, where and how are these particles accelerated to such high energies. So cosmic rays were detected, but look out in space and have theories for how they might be accelerated, often in shock fronts, and the energy from the shock front basically is passed onto the particles through sort of iterative processes that they accelerated up. So kind of look at models and look at the magnetic fields that would be needed, the size that would be needed to accelerate the particles, and think of particular objects that might do the job, but we didn't actually know where they're coming. And as I said, these cosmic rays are detected, and here's a shower, and you can see from that shower, like we do with the neutrinos, you could work out the direction of the cosmic ray as it entered the atmosphere. But the thing about cosmic rays is they're electrically charged. They're basically they're the nucleus of atoms, not neutral atoms. So some are protons going up to ion nuclei, and anyway, they're positively charged. And positively charged things get bent in magnetic fields. So there are magnetic fields in space and around our sun, but there are magnetic fields in our galaxy, and they basically scramble the direction of those cosmic rays. So this is a cartoon of a cosmic ray that may have been accelerated in some object like this, and even though this one happens to come and interact in our atmosphere, and we detect it and we deduce something about its energy, we don't know where it came from, because this direction is that it enters our atmosphere has no longer anything to do with the direction where it came from. So we're detecting these cosmic rays, but we don't know where they're coming from, because of this fact that their path is bent by magnetic fields. So what about the neutrino? Neutrinos, idea is that cosmic rays, pretty much inevitably, when cosmic rays interact, they produce neutrinos. So if a cosmic ray interacted in the environment near its source, and we presume some should, probably quite dense sources, obviously not all of them, because we detect some of them on Earth, and we're presumably not getting all of them. So some of them definitely don't, not all of them interact, but some of them we would expect to interact. They interact quite readily when there is matter or light around for them to interact with. And when they interact, they really produce neutrinos. So that was kind of the proposal for building IceCube, is that there should be these high energy neutrinos associated with cosmic ray interactions near their source. And these neutrinos, as we talked about, they're neutral, not bent by magnetic fields, hardly stopped by anything, because also will photons be produced, and the high energy, the gamma rays. But gamma rays actually interact pretty readily. So once you get up to the highest energies, it's actually only neutrinos that can be a direct messenger, a messenger that points back in direction and doesn't get absorbed from the high energy universe. So neutrinos are our only direct messenger from the highest energies. So here I have a little bit for those who do know some particle physics, for the interactions of cosmic rays. When they interact, they produce some other particles called pions, and the charged pions, when they decay, they produce these neutrinos. And so these are the interactions that we expect to happen. But if you've never heard of a pion before or any other thing, all you need to know about is that there's these high energy cosmic rays. We want to know where they come from, and we expect some of them will interact near their sources and produce neutrinos. So that's why IceCube, now obviously not to size, but was built to detect neutrinos. Some of them will pass through, some of them will interact and give us one of these tracks, and we can detect them. So that was why IceCube was built, and I told you about how we would detect neutrinos. And now I'm going to tell you about backgrounds. So pretty much every particle physics experiment has backgrounds, which means that you see not only what you want to see, you detect more than your goal. So we want to see astrophysical neutrinos, but those cosmic rays, when they interact, and I said they produce these showers of particles, they produce muons as well in this shower of particles, and we call them atmospheric muons because they're created in the atmosphere. There's also atmospheric neutrinos created in these showers. So in IceCube, these muons, they can travel some kilometers, so they can get down into our detector. And so we actually detect many of these backgrounds. So this is the rate, so it's 3,000 hertz, so 3,000 a second. So this huge 275 million of these muons we detect in our detector daily. And there are also these atmospheric neutrinos, which are interesting as well, but they're not the astrophysical neutrinos that we were aiming to see. And there is around sort of 8,000 of those because they're produced with these, well, along with these muons, around about as many as these muons, but of course they don't interact as much. And so we see around 8,000 of those atmospheric neutrinos in our sample as monthly, but it was probably only tens of astrophysical, the neutrinos that we're after per year. So this background is a real needle in the haystack problem that we have in our detector. And so this is a kind of, I guess, maybe not so exciting part to talk about in a detector, and it's not just that I wanted you to share the pain or the difficulty here. I mean, a problem shared is a problem halved, and it would be nice if I shared it and it was halved and I could halve it again and halve it again, it might go away. But that I wanted to share it really because that I think it helps to understand the process that we go through to analyze and study our data, why we can't just see a neutrino straight away and say, hey, that's an astrophysical neutrino, that must be coming from the source. Because when we see the neutrinos, we aren't actually always sure that they are astrophysical neutrinos. They could be this atmospheric neutrinos. So we have to be careful. And we also have to, when we get a signal in our detector, most of the time it will be these muons here actually. So we can't just send off alerts to other detectors, say just straight off to look every time we see something. They do not want to get alerts 3,000 times a second to telling them to look at something which has nothing to do with astronomy at all. So this is why we have to operate much the way we do with IceCube. And if you see or read any of the papers, a lot of it you can understand the way we analyze is to do with these backgrounds. But it's a needle in the haystack, and if you've got a needle in the haystack, you can get a magnet and you can probably get the needle out. And so we've got some techniques for getting those astrophysical neutrinos out, or neutrinos at least for a start. So and this one of the things is we can look for upward going tracks. So in this slide, I've got the Earth. You guys, I think most of you in the northern hemisphere, you're here somewhere. I'm kind of halfway to the South Pole. And here's the South Pole, and there's our detector. And these red arrows are demonstrating cosmic rays, and the blue ones are neutrinos. So this is an astrophysical neutrino coming from a source when a cosmic ray interacts near its source, and this is the guys that we're after. This is one of these cosmic rays that comes and it interacts, comes on some bent path, interacts in our atmosphere and produces a muon. And this is one happened to interact in our detector and also gave us a muon. These are the ones that we see 3,000 a second. These are the ones we see tens of per year, and we want to try and tell them apart. And this is kind of hard because they're coming down. But if we look for tracks that are going up, so now we have some of these astrophysical neutrinos coming here from some objects and produce some muons. Here we have the protons now interacting up above you somewhere, up above Britain somewhere. They produce those air showers, which have muons and atmospheric neutrinos. These are atmospheric neutrinos in them because they're created in our atmosphere. Both of them from cosmic rays interacting. We call them astrophysical neutrinos when the cosmic ray interacted near its source, and we call them atmospheric neutrinos when the neutrino was created in our atmosphere. But the muons, they can't travel very far through the Earth. So if we see something that's coming up through our detector like this, we know it's come from a neutrino, because nothing can get through our Earth and have a path going up other than a neutrino. So these can't be these atmospheric muons, these ones. They have to be neutrino muons. We don't know whether they're atmospheric neutrinos or they are astrophysical neutrinos this way, but we do know that they are neutrinos. So that's one of our big strategies for a start for getting rid of that muon background as we look for things going up. We have another one as well where we can use the outer parts of our detector as a veto. So here the idea is that if you have some cosmic ray air shower that produces some of these muons, the muons coming into our detector, so this is a kilometer down, they come in and they're producing light all the way. And so there'll be some light detected here, some light detected here, so on. As opposed to a neutrino that interacts in our inside our detector. So we call these starting events. So we look for starting events which are ones where the first light that's detected is detected well within the detector. So we look for where the first light that we see associated with the event. And if the first light is on the outer part of the detector, we say, no, veto, we don't want you. You're probably might not be, but you by chance, because there's so many more of them, you're probably one of these atmospheric muons. But if we see the first light within the detector, then we say, okay, that was a neutrino event because the neutrino interacted and then produced the muon. So that's another separate technique that we can use that also allows us to see things coming down into the detector. And here is another way we can separate astrophysical and atmospheric. And here I'm going to tell you again about those spectra. And this is maybe a little bit, but I'm and it's well into my talk, so hopefully you're up for it. But there's a little bit of maths, I guess. It's not really, but I'm going to go graph again. So it's a flux, the amount that you see graph versus energy. And the thing is that the atmospheric neutrinos, so this is in log, so that means this is a e to the power of something, and it comes out as a straight line on a log graph. People used to looking at COVID cases. Now you're probably always seeing log graphs because unfortunately the cases go up in exponentially, and so you see these things on log graphs instead. And so this is a log graph. So it's the log of the flux. So we can see basically the number of atmospheric neutrinos as a function of energy here. And on a log graph, it has a different slope compared to astrophysical neutrinos. So if we start detecting neutrinos, we can't tell them necessarily on a one-to-one basis which one is an astrophysical, which one is an atmospheric, but depending on the energy, we can have a good probability of one or the other. So this was a prediction that now we're starting to get observations from IceCube, but originally when the detector was proposed, it didn't know where this line would go. But so this is one way that we can look. And so if we're looking at particularly high energies, then we say it's very probable that that's an astrophysical neutrino. Lower energies, it's probably an atmospheric neutrino, and somewhere here it could be either. So that is this difference in the number of them as a function of energy is one thing that we can use to help us determine that whether we've seen astrophysical neutrinos or not. So that we did see. So we built the detector, and actually soon after, it took us a couple of years to analyze and really believe that we had seen what we had seen among the background. But we break through with the first astrophysical neutrinos detected. And now thinking about this graph that I showed you, this kind of is something like what the data looks like. So these black dashes are indicating our data now as a function of energy. And so the black ones are just what we see, and then we can see we fit one line and then another line. So we're basically seeing the slope change, and this is our evidence that we have a different type of neutrinos coming in, not just the atmospheric ones, which have been seen by other detectors as well, but we are now seeing at the higher energies a different component coming in as well. So this is basically our evidence that we have seeing these astrophysical neutrinos. So that was back in 2013, and so we had lots of now of these tracks. As I said, you can't tell for each one for absolute sure it's astrophysical, but the higher energy it is, the more likely it is to be astrophysical than atmospheric. So great, so we've detected the neutrinos. Now let's see where they point back to and discover the sources of cosmic rays. So that's what we tried to do. And at first, they didn't really particularly line up anything. So in chance, if you have a neutrino, there's a lot of stuff out in space. And so if you look there, probably it will line up with something, but you don't know if that's just by chance. I mean, if I point there, probably I will see something. Is that for sure that neutrino is associated, because we know neutrinos can come basically across the universe, so they could be coming from anywhere far back. So we do things like correlation studies where we look and see whether our neutrino events are correlated with a kind of object, and we also look for hotspots in our own sky. So that's what this graph is about. This is us searching in all our neutrino events, some of which will be atmospheric neutrinos, many of which will be atmospheric neutrinos. But we look in each, we kind of pixel up the sky and we say, how many events have we got in there? And we look at the energy of those events and we see what's the likelihood that there is actually a source, because the atmospheric ones should be quite smooth across the sky, but if it's an astrophysical source, it should see as a hotspot. And we were doing that pretty much as soon as we were getting our data, and we weren't seeing any of these sources. As I mentioned, we also did correlations with various types of astrophysical objects. So this is the Fermi telescope, which is a gamma ray telescope, and it's detected lots of active galactic nuclei, which I'll talk a little bit more about in a little bit. And these are the ones that they have seen. And so we cross-correlate our neutrino events with these to see if they happen to be more than by chance, that the fact that these are lining up. And again, we didn't see anything when we did that. Some will line up by chance, but not more than would be expected just by random correlation. So we also have, and along with that, we had an alert program, because these other ways weren't working, and we're still doing those things. And I'll tell you, we actually have started to see hotspots as well. But what we do send is alerts. So when we see neutrinos that we believe at least 50% likely to be astrophysical, we send alerts out, and there's tens or so of, not much more than 10 of these we send out per year. And that was got jackpot for back in 2017. So then we got neutrinos associated with a blazar, which is one of these active galactic nuclei that I'll talk about. So here is the event that was detected on September 22nd, 2017, and we sent out, as I said, which we do around 10 or 12 times per year, one of these alerts. And other kinds of detectors had a look. So this was the Fermi telescope. So they actually noticed that this neutrino, here is our neutrino event that we detected here, lined up with this object, which has this name here, which is an active galactic nuclei. Also, the MAGIC telescope, which is a gamma ray telescope, but for higher energy gamma rays than Fermi looks at. We also noticed that there was high energy gamma rays from this object. So as I said, it could be by chance that a neutrino could line up with the active galactic nuclei. If you remember back on the one I showed of those Fermi detected active galactic nuclei, there was quite a lot of them. So it could be by chance. But that actually happened. This was one of the highest energy objects in the sky at the time. It was flaring at the time. It was having a particularly high energy time. And so that is less likely to be just by chance that this neutrino lined up. And then it was producing these particularly high energy gamma rays that were detected by MAGIC. So we believe this association was real. And so I'll just tell you a little bit about active galactic nuclei. This is an artist's picture. So what it is when you have a supermassive black hole at the center of a galaxy, and so around a supermassive black hole you get a disk of accretion disk, it's called. So if something's falling into a black hole and it goes going straight in, it will fall into the black hole. But if it's going to miss, then there's this, for the physicists, I'm sure there's someone that it has angular momentum, and so angular momentum has to be conserved, and you form a disk around. You have this accretion disk. And then within that, you have charged particles, you have magnetic fields, and you get a bit like a tornado where you have a sort of dust, and then the tornado, which is also to do with conserving angular momentum, you have jets. And so there's many of these active galactic nuclei, and when the jets are pointing at us, they're called blazars. And this object was a blazar with a jet pointing at us, and was particularly high energy at the time. And so we worked out, and we thought that wasn't likely to happen by chance. It might be, but we think that neutrino was associated. And these objects are somewhere we suspected that cosmic rays could be accelerated, and neutrinos then could be being produced by those cosmic rays. So that was another breakthrough, in that we had perhaps opened or solved at least a step towards solving that mystery of where the cosmic rays are coming from. Another association that was reported was a neutrino that we observed in 2019 in October, and then people looked in that direction, and they saw that there was a tidal disruption event earlier in 2019. So that's when a star is, so not as massive black hole as these active galactic nuclei, but a massive black hole, and a star being ripped apart by this massive black hole. And so they said, that these were associated, and then this neutrino produced there. This is actually a little bit in doubt from now there has been radio observations of this black hole. It's just still feeding, and it doesn't seem from those observations that there's enough energy there to produce this neutrino. So I think the jury is maybe out, and maybe it's actually unlikely, and this might have been a chance coincidence. But these are things we definitely still want to study. I mean, maybe there was something particular at that time that allowed the neutrino to be produced, and now in general the radio emission would suggest that it's not high energy, but yeah, there's definitely some more work to be done. And I mentioned we're still looking in our own data, and we actually see now starting to see hot spots in our own. So we're seeing enough neutrinos of sort of sufficiently energetic ones that that they're sticking up as being more than we would expect just by chance from this region where there is an active galactic nuclei. So we might be actually just seeing that coming now. It takes some time for us to amass enough data for the little spikes to be accumulate enough above that background of those atmospheric neutrinos. So we think we are making progress, and we're seeing that as top candidate are these active galactic nuclei, these supermassive black holes at the centers of galaxies, which are feeding and with their jets. So I think I've sort of gone over the hour that I was going. I hope you're still here with me. But so I guess in summary, I hope what you've taken away from this research is it's super exciting, and that neutrinos are really unique cosmic messengers from the high energy universe. So because of their kind of unique ability not to get their paths bent and to get right across space, we can use them to study high energy objects. At the moment, for a start, we were trying to figure out where they might be coming from, because that would tell us where cosmic rays are coming from. We now want to detect more of them so we can study their properties and learn more about those acceleration processes, and which AGNs, because it's obvious that not all active galactic nuclei are producing neutrinos. What is it special that allows is it just in certain phases? Is it certain characteristics about some of the objects that allow cosmic rays to be accelerated to those highest energies, and then we see those neutrinos. So yeah, I'll stop there, and I hope there are some questions, and I hope you can carry on following our research as we go on, because I'm excited we'll have more exciting results to share in the future too.